Welcome back. In this video we'll continue working in section 4.2 where we're talking about least squares regression. And we'll continue in this video to talk about the least squares regression line, and we'll use the line to make predictions. Now, in our last video we took a small data set of 6 points, created a scatter plot, and we plotted a straight line through the 6 points. And if you'll recall, the way that we came up with the straight line was that we simply picked 2 of the points and then figured out the equation of the straight line that passed through them. Now we could imagine using the line to give us a prediction of the value of y for any x within the range of the x values in our data. So for example, if x equals 3, then we can say that the predicted value of y when x equals 3 is 4.75. That's the value of y on the line when x equals 3. But since we already have an observation in our data where x actually does equal 3, then we can think about how much our straight line model misses this actual data point. Now we calculated that miss by subtracting our predicted y from the observed y. That's 5.2 minus 4.75, and we call that value the residual, or it's sometimes called the error, for that data point. And that brings us to the idea of how do we figure out the best fitting line to model these points. Now recall that the line here in our example, we sort of pulled this out of thin air by choosing 2 points from our data and simply finding the line that goes through them. Now that's not a terrible idea, but the actual way in practice that we determine this line is through something called the least squares criterion. And what the least squares criterion says is this. For each observed point in our data, we can calculate the residual, or the error, that we'd get with any particular line. Now, imagine that we square the residuals and then add them up. That is, we sum them across all the points in our data. Well, that gives us a measure of total error in our model. That is, it's a measure of how much our model misses the various data points. And now, using some tools from calculus that we're not going to get into in this course, we can determine what's the one single best line that gives the least possible error. That is, the line that minimizes the sum of the squared residuals across all of our data points. And so this is what's called the least squares criterion for determining the best line through our data. It's the line that gives us the least possible sum of squared residuals. Now, there are formulas for determining the least squares regression line. That is, formulas for determining the slope and y-intercept of the line. But first, let's think for a second about the general form of the equation of the line. The general form of the equation for the regression line is y hat equals b1x plus b0. Now notice that this is the same general form as the slope-intercept form when we say y equals mx plus b. But here we're denoting the slope as b1 and the y-intercept as b0. Now you'll notice that we've also got a caret symbol over the y in our equation. That's to emphasize that the y in this equation is a predicted value. In other words, once we come up with the appropriate values for the slope b1 and the y-intercept b0, then we've got the equation for a straight line, but the y values in the straight line are the predicted values for y. Now we call this notation y hat. In fact, it's quite common in statistics when we're talking about a predicted value to use this hat notation. So, we'll say that the general form of the equation of our regression line is y hat equals b1x plus b0. However, we'll often write y hat equals b1x plus b0 as y hat equals b0 plus b1x. In other words, we're just interchanging the two terms on the right side of the equation, and that doesn't have any effect on our regression line. This is just a common way to write the equation. Now, let's think about the calculation of B0 and B1. There are formulas in your book for how to calculate these values. However, we're not going to ask you to calculate these values by hand. We're strictly going to let the software do the calculations. Now, in a more advanced course, we might think about where these formulas come from. But in our course, it's going to be enough to say that these formulas for computing the slope and the y-intercept of our regression line are guaranteed to give us a line with the smallest possible sum of squared residuals. That is, looking across all the points in our data, these formulas will give us the best fitting line. So now let's pull in some real data and calculate our regression equation. Let's consider one of the data sets we used earlier. This is the data set where a family doctor has collected data on the age and total cholesterol of 14 of his female patients aged 25 to 65. We've made this data available to you as an Excel file that you can pull into either StatCrunch or Minitab. Now, we can put this data into a scatter plot, and we see that there appears to be a positive linear trend to the data. As age increases, total cholesterol tends to increase in a fairly linear manner. But now, though, let's estimate our least squares regression line through this data. So I'm going to pull this data into Minitab and use the regression procedure to obtain the least squares regression line. Note that we're considering total cholesterol to be our response variable and age to be our predictor variable. Now, we have separate videos that detail all the steps for using Minitab and StatCrunch for regression. After you watch this video, you should watch those videos to see the detailed steps involved, and then you're going to want to pull up some of these data sets and run them through the regression procedure for practice. So now, after we run the regression procedure, we get the following output from Minitab. Now, much of this output we're not going to worry about, but there are a few key things here we're interested in. First, we have the regression equation. Total cholesterol equals 151 plus 1.40 times age. Now, total cholesterol is our y variable. That's the variable we're going to want to predict. 151 is our y-intercept, and 1.40 is our slope coefficient. So notice that this is in the general form for our regression line, y hat equals b0 plus b1x, where b0 is 151 and b1 is 1.40. And notice that the value of b0, the y-intercept, is given here in the column of coefficients. Although you notice that here Minitab is giving it to a couple more decimal places. And just below it is the slope coefficient b1, which, given to a couple more decimal places, is really 1.3991. So if we think back to our scatter plot, then our least squares regression line can be plotted on top of our data points. And now let's use this equation to predict the total cholesterol for a 42-year-old woman. So our regression equation is predicted total cholesterol equals 151 plus 1.40 times age. We plug in 42 for age, and we get predicted total cholesterol is 210. So, in other words, our predicted total cholesterol for a 42-year-old woman is 210. Now, we can get Minitab to calculate this predicted value. Within the regression procedure, I'm going to want to click on the Options button. I get a new dialog box, and I'm going to enter 42 into the field that says Prediction Intervals for New Observations. Again, we walk through these steps in a little more detail in our videos on using Minitab for regression. Now, I'll click OK, and then I'm back in the regression dialog box. Click OK again. And now I'm going to move over to Minitab here so that we can more easily see the regression output. And you see that in the session window, as I scroll up, we have our usual regression output, and this all looks just the same as what we had before. However, if we scroll down the output, we have a new section called Predicted Values for New Observations, where we've set our predictor variable, age, equal to 42, and just above it we have our predicted value for total cholesterol, what Minitab calls the fit value of 210, just as we calculated a moment ago. Now, I'll recommend that you pull in this age cholesterol data into Minitab and try to replicate this analysis. And then I'll also recommend that you pull the data into StatCrunch and use that software to calculate the regression equation. Your output in StatCrunch should look like this. Now again, much of this output we're not going to worry about at this stage, but I'll point out that we still get our regression equation, and you'll notice that the regression coefficients, that is the intercept and the slope, are exactly the same as what we obtained from Minitab.